Good morning, student. Welcome to Urban Pro. So today we are going to discuss a topic which is interesting again. Listen. So today we'll be actually discussing on mass defect and nuclear energy. So our discussion will be on the root cause of nuclear energy, the energy of star, the energy of nuclear weapon, the energy of nuclear reactor. Okay, so let us start our discussion today. So mass defect and nuclear energy. So we will start with mass defect. What is mass defect? There is actually no as such defect in mass, but still this mass defect is actually none other than the difference between two masses. Difference between what two masses? See, it is all about nucleus. Suppose this is a nucleus, and as you know, there are protons or neutrons inside a nucleus. Here I have taken 1, 2, 3, 4, 7 protons, and let us take some neutrons. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I have taken here 7 proton and 8 neutrons in a nucleus. Okay, so mass defect is, listen, according to our daily knowledge, what we will say, what is the total mass of the nucleus? Suppose total mass of the nucleus is m, and what is the total mass of the neutrons and protons? As I have written here, 3, 5, 6, 3, 4, 5, 6, 7. 7 proton, that is 7 mass time proton plus 8 mass time neutron, isn't it? So our daily life experience, our common experience will say that mass of the nucleus will be equals to the total mass of the protons and neutrons. But it is actually wrong. The experiment says it is the mass of the nucleus is less than the total mass of the proton and neutron. Then so here what do we see? There is some mass is missing. So let us name it as missing mass. Let us name it as missing mass. Actually, in technically we say this is mass defect. Mass defect here is what? It is the which one is greater? Here greater is the 7 mass of proton plus 8 mass of neutron minus mass of nucleus. This is mass defect, or we are saying missing mass. Okay, so let us define it first. It is nothing but the uh, sum of sum of mass of nucleons nucleons of a nucleus minus mass of nucleus. Okay, mass of nucleus. This is mass defect, and we are naming it as missing mass. But actually there is no mass is missing. No missing of mass is there. No missing of mass is there. Mass actually gets converted into energy. Mass actually gets converted into energy. Okay, and that energy is known as binding energy. Binding energy of a nucleus. Okay, so let us discuss now the binding energy of a nucleus. So heading is binding energy. What is binding energy? I already told, it is the energy corresponding to a mass defect. So let us write it in word. So binding energy is corresponding corresponding mass corresponding not mass corresponding energy corresponding energy to mass defect, mass defect of nucleus. Okay, so it is fine going into binding energy, but it will be better if we now discuss the how we will get the corresponding energy to a mass that is governed by Einstein's mass energy relation. So Einstein's mass energy relation. As you know, there is a famous relation E is equals to mc square. So this is the Einstein's mass energy relation. What does it mean actually? If you have some mass m, then when it will be converted into some energy, the amount of the energy will be mc square. What is c? C is the speed of light, 3 times 10 to the power 8 meter per second, and this is a very large number. When we will take the square of this large number, that will become more large, isn't it? 9 into 10 to the power 16 is very large number. So now if we take a very small mass here, delta m, as we are multiplying c square, very large number, with a very small mass, then also it will give a large mass, then also it will give a large energy, large energy. So we can write it in words that even a very minute mass releases very huge energy. We will take an example that will be better. That will be better if we take an example. Okay, it will be better if we take an example. Suppose helium 4 is a nucleus. How many protons and neutrons are there? 2 protons and 2 neutrons are there. Okay, so let us calculate, let us find mass of 2 proton and 2 neutron is equals to what? It is approximately 4.032 U. What is U? U is the atomic mass unit. It is a unit of mass, and it's how it related with kg. It is approximately 1.66 times 10 to the power minus 27 kg. Okay. Okay. Now we'll take mass of helium 4 nucleus is equals to what? It is approximately 4.0026 U. Now what is the mass defect? Corresponding mass defect is equals to 0.0294 U. Okay. See, according to the Einstein's mass energy relation, what is the corresponding energy of 1 U? Isn't it? There is a energy corresponding to every mass. So what is the energy corresponding to 1 U? It is nothing but, if we write here 1.66 10 to the power minus 27 kg, and c square, that is 3 into 10 to the power 8 square, we will get it as 931 mega electron volt. Okay, mega electron volt. So now we will check what is the energy corresponding to the mass defect of helium nucleus. So we have to calculate 0.0294 multiplied by 931 mega electron volt. If we calculate it, it will come approximately 27 mega electron volt. Now just imagine how much small the mass was. It is 0.0294 U. In kg, it is 1.66 into 10 to the power minus 27. A very small mass is this, isn't it? 1.66 into 10 to the power minus 27. Just imagine how small this mass is. And this is giving 27 mega electron volt. Mega means 10 to the power 6 is there, isn't it? So as I have written here, Even a very minute mass releases very huge energy. So this is the proof. Okay. Now let us come back to binding energy. As I told, that corresponding energy to mass defect of nucleus. It is also defined in some other way. Like suppose you already have a nucleus. You already have a nucleus. So you have this nucleus and you want to break it into its constituents, elements or nucleons. So let me paste it here. Suppose this is the nucleus, isn't it? Now you want to split into its constituent nucleons. That is how much proton is there? 1, 2. Okay, how we will break it? We'll copy it and we'll paste it. Okay. See, now we will take one and again one and another, and we will keep them in large distance just to mean that these are now splitted. These are broken. The nucleus is broken. The nucleus is broken. Now we will check. Okay. I hope you understand what I want to do. Okay. So it is the you can't do it without any energy. You have to put some energy, and that energy is equals to binding energy. So energy required to break a nucleus into its constituent nucleon. Okay, I hope it is clear now. In some other way we define binding energy. What is binding energy? The energy equal to the energy released when a nucleus is formed. So when the nucleons are combined to form a nucleus, some energy is released, and that energy is also known as binding energy. So what do we see in binding energy? We see that whenever a nucleus is formed or is broken or splitted, then the binding energy comes into play. Now, similarly, the fashion is same. Similarly, whenever a nucleus is splits into, okay, is splits or gets combined, energy is released. Energy is released. That energy is known as nuclear energy. We'll discuss now nuclear energy. So what is nuclear energy? Nuclear energy. Basically, the energy released in nuclear reaction like fission and fusion. Fission and fusion. Now definitely we'll discuss what is fission, what is fusion. So fission is a nuclear reaction, that is definitely there is maybe some combining of nucleus or splitting of nucleus, but in case of fission, actually a heavy nucleus splits into splits into two lighter nucleus, releasing energy. So when a heavy nucleus is splits into two lighter nucleus, energy is released. Definitely that energy is nuclear energy. And we see this, where do we see this fission? Here the nucleus, for example, the nucleus is uranium 235. Where do we see this nuclear fission? In nuclear reactor. In nuclear reactor, the fission is taken place. Next, nuclear fusion. When, okay, not when two lighter nucleus combine into a heavy nucleus, releasing energy. This reaction is known as nuclear fission. Fusion. Okay. Where do we see combine the lighter nucleus? That is, the lighter nucleuses are hydrogen isotopes. Okay. Where do we see that this fusion? We see in stars. Okay. We see in stars. In stars, the nuclear fusion is taken place. So let us conclude here by just giving you the conclusion. So we started with mass defect, which is the cause root of nuclear energy, the energy of nuclear weapon, energy of star, energy of nuclear reactor. And here we see that even a very minute energy can release very huge, large energy. Then we see the Einstein mass energy relation, which actually the connection between the matter and the energy. And finally, binding energy and nuclear energy, as I told. Hope you all understood the topic. If you have still any doubt, then do contact with me through my profile in Urban Pro. See you in the next session.